Hello everyone. In this video we are going to be using Excel again to help us out do confidence intervals, but this time with proportions. So let's take a look. It says Dax is out trying to do a study on the proportion of individuals in Casper who went hunting this season. He randomly selected 229 people from the community and had them report whether or not they hunted this year. He decides to make a confidence interval to approximate the proportion of people hunting this season. He wants to have a 99.5% confidence interval. Okay, let's grab our data first. We're going to go ahead and copy all of that. And let's go ahead and paste it into, go ahead and paste it into our cell. We'll do a paste special as text. And we have whether or not you hunted this season. And we are interested in to have a confidence interval of the portion of people who did in fact hunt this season. Okay, so let's go ahead and do this again, looking at our data variable statistic, population, parameter, and sample. Remember, I like to do population and the parameter first. So let me kind of minimize this so I can see a few more things. So let's start off with the population. So that's all the people going to be living in Casper. That's going to be letter D. The parameters, the truth about all of those people. So it's going to be the proportion of all the people who went hunting in Casper. So that's going to be letter E. Didn't select it, letter E. Let's now do our sample, which is F. So that is the 29 Casperites who were measured, F. Let's do our statistic, which is C, which is going to be the proportion of the 229, which is going to be right here, letter C. The data is the list, so we'll do that as A. And our variable is this, like whether or not if someone went hunting this season. So we'll call that letter B. Excellent. We got through those. And let's go ahead and dive into our confidence intervals. So we want to know that Dax knows that he can only use the normal approximation here in certain circumstances. Is he good to proceed with the calculations? This is back on our second page of our cheat sheet, and we need to know, are we dealing with numerical or are we dealing with categorical data? So let's do just a little bit. Let's label our variable. And we'll call this like hunting, and the answers are going to be yes and no. So the data type is categorical, and specifically this is dichotomous, which means that we just have two options. Okay, so since we're dealing with categorical data, we can look at our categorical proportions and our central limit theorem rules, and says the sampling distribution of P is approximately normal if both the number of successes and the number of failures is greater than or equal to 15. Well, we don't know what pi is. We don't know what the true proportion is. That's what I'm looking for. So instead of using n times pi, I'm going to use n times p. So I'm going to need a sample proportion in order to make this check. So first things first, are we dealing with numerical data? Well, we said no, we're dealing with categorical. So we're going to jump down to our categorical, and now let's jump into our key variables. Let's see what we've got. So the confidence level was our first one. I think it's back up in here. We want to have a 99.5. So let's do confidence level equals, and we'll do 0.955, 95.5. We know then that our alpha level is going to be equal to 1 minus that confidence level. Next thing I want is my sample size. So I'm going to say n equals, and to get that sample size, we're going to do count A. So we'll say equals count A. And let's go ahead and select the data. So I'm going to select on the first one, Control Shift down, parentheses, and I am going to copy those real quick, Control C, so that I have that range. I'll hit enter. So the sample size that we have is 229. So I'm going to label this first one as K yes, as the number of people who said yes. And I'm just going to do equals count if. Count if is a really good function. And I actually don't have it here. I'll probably post it up in just a little bit. But count if is what we do. We're going to put in our range. So I'm going to say, okay, look at all this range and count if it says yes. And I just clicked on, it doesn't matter which yes you click on. I'm just going to say, how many yeses are there? And we have 92. And I'm going to say K of the no's is going to be equal to equals COUNTIF, same range, and this time I'm going to click on no and see how many no's we have. So you see I have at least 15 yeses and I have at least 15 no's, and so I am good to proceed. So our sample proportion that I'm interested in, I'm going to go P of yes, because I'm interested in the proportion of people who actually went hunting. And in order to do that, I'm going to take the number of yeses divided by my sample size. And so my sample proportion is 40% of people in Casper went hunting this season. So the next thing that I want is my standard error. So what's a little bit different than this is when we did our standard error with proportions, when we were just dealing with our sampling distributions, we used pi in order to help us calculate the standard error. But here we don't have pi anymore. We only have our sample proportion p. It's our next best thing, and so it's what we're going to use for our standard error. So here we're going to do the square root of p times parentheses, don't forget your parentheses here, 1 minus p. And we're going to divide by the sample size, and we'll end our parentheses there of the square root, and that gives us our standard error. The next thing that I'm going to do is I'm going to get both of these z distribution, the two-tailed and the one-tailed. You will always use the z distribution when we are doing confidence intervals with respect to proportions. So I'm just going to call this a z two-tail, and I'll call this next one z one-tail. And they're very similar in our calculations. We're going to do norm.s.inverse. And we only need to put in the probability, which is just for the two-tailed, we're going to do 1 minus alpha divided by 2. And we hit enter. And for the second one, we're going to do norm.s.inverse of just 1 minus alpha. So on the two-tail, we divide alpha by 2. On the one-tail, we just leave it as is. And we hit enter. Then the last little thing that I've got is I've got the margin of error. And the margin of error is very simply going to be the z two-tailed times the standard error. And that gives us our margin of error. Okay, at this point, I have all the key variables that I need in order to do all of my calculations. Let's go ahead and scroll down and look at some of these other questions that we have. So the first one that we need to know is like, provide an answer of like, are we good in order to do this? So we can say that, yes, since the number who responded yes is 92 and the number who responded no is 137, they're both are at least 15, then the sample size is sufficient to invoke the central limit theorem. Next one is our best point estimate. Well, if you remember from our previous video, when we did means, our best point estimate was our sample mean. Well, here, our best point estimate of pi, we'll say, is p. So this is our best point estimate of pi. And it's that just 0.4175. And there it is. We want to provide the confidence interval. So we weren't given any directionality here, so we are going to do a two-tailed interval. And we need a lower and an upper. And while I'm at it, we're also going to do a one-tail lower. And we're going to do a one-tailed upper. And let me just copy these. We'll paste them there. We'll paste those guys over there so that we can show how we can do each and every one of these. Now, typically in a problem, we only provide one of these confidence intervals. We're only interested in either doing a two-tailed or a one-tailed lower or a one-tailed upper. This is just to get us practice. Okay, over here in our confidence interval, so we know that we're dealing with categorical data proportions, so we know our sample proportion P. We've gotten all of our key variables, we did everything, so now we can just come over and plug things in. So for our two-tailed interval, all we have to do is take our sample proportion minus our margin of error, and that's it. And for the next one, we take our sample proportion plus the margin of error. So for this one, we double check our answers, 0.3 0.3668. Yep, that looks good. And 0.666. Yep, that looks good too. Is this confidence one-tailed or two-tailed? We know that it's two-tailed. And down here, we can use these confidence interval statements again to help us out. So we are 95.5% confident that the true proportion for people in Casper who went hunting last season is somewhere between 34% and like 47%. And if we look at this, that's exactly the correct option here. Now remember, we have some like decoys in here. Remember, we don't want to say that there's a 95, that there's a chance that's there, and nor do we want to talk about the sample proportion. We want to be sure that we're talking about the true proportion. Okay, here it says, suppose instead we wanted the confidence interval for at least. Now remember, let's do just a quick picture. This two-tailed confidence interval, when we draw it out, looks like this, right? We have our confidence interval. We're going to center this thing on the sample proportion P, and we did a two-tailed where this is like our middle 95%. For a one-tailed interval, we're going to say that we are 95.5% confident that we're at least some value. Well, at least says that we want to be from some value or greater. So we're going to do a one-tailed lower tail, because notice this lower tail is where we could be wrong. Let's go ahead and see what we need to do in order to calculate that lower tail. Check this out. It's going to be very, very easy to do. The lower tail is just equal to our sample proportion minus that Z1 tail times the standard error. And that is our new lower bound. And our upper bound, if you notice, is 1. And you might be thinking, like, wait a second, I thought the normal distribution extended from positive infinity to negative infinity. And typically, like, yes, that is true. However, when we are dealing with proportions, we know that proportions here can span only from 0 to 1. So if we have a lower bound on it, it'll say 0. And if we have an upper bound that goes like all the way to infinity, technically infinity, it will be a 1 here. So if we look at these options, we were able to knock those out of the park and get those. So this one is a one-tailed interval. And if we select the appropriate decision, again, if we go down and look at the lower tail option, so we are 95.5% confident that the true proportion of people who lived in Casper who went hunting this season is greater than 34, like 35% if we round up to 2 decimal places. And we can see the right answer right there. All right, this last one, it says, suppose instead we wanted the confidence interval for no more than. Okay, well, no more than means that we are going to give to this little bound an upper side and say that, hey, we think that it's no more than or less than a particular value. Excellent. This one, we want a one-tailed upper where the lower bound is now 0. And we're going to give an upper bound for here, our sample proportion. We'll say equals our sample proportion plus the Z1 tailed times the standard error. That gives us 45%, 46% roughly. This is one-tailed, and we are 95% confident. Here, let's go down to that little help out. 95% confident that the true proportion for Casperites who went hunting this season is no more than 46%. Okay, so that's how you handle proportions. Proportions is no harder than dealing with means. The key thing is we go through, we grab our key variables, and then we just plug them straight into our equations, and we're able to get our confidence intervals out. That helps you out. Best of luck.